Okay, good evening, students. We're looking at hybridization and shapes of molecule. Now, before considering a topic like this, it is already taken for granted that you have understood bonding very well, okay? Because it's important you know your various bonding, your interatomic bonding, and your intramolecular bonding. Of course, when I talk about intramolecular bonding, it's also known as interatomic bonding, which falls under your covalent bonding, your ionic bonding, your metallic bonding, and your dative bonding, known as coordinate covalent bonding. And then when I talk about intermolecular bonding, I'm talking about your hydrogen bonding and your van der Waals. Let me say it again. Probably I made a mistake. Your bonding is divided basically into two. Your intramolecular bonding, also known as interatomic bonding, and then we have intermolecular bonding. So if I call it intramolecular bonding, I'm also calling interatomic bonding. Now, when you understand the bonding very well, and you look at the shape of the various bonding of various compounds, then that will help you when you are coming to shape of molecule and of course hybridization. So for today, we're looking at hybridization. What is hybridization? Hybridization, hybridization is the blending or the mixing, the blending or mixing of two pure atomic orbital of the same energy level, to form a new hybrid. The blending or mixing of two pure atomic orbitals of the same energy level to form a new hybrid. That's what we call hybridization. And at your level, we have various hybridization. We have the XP3 hybridization. We have the XP2 hybridization. We have the XP hybridization. We have the XP3D hybridization. We have the XP3D2 hybridization, and so on and so forth. Of course, when you get to 100 level, maybe even at 200 level, this is a topic that you will deal with, chemistry in particular. So you're going to be dealing with this if you're schooling Uniben and maybe some other school like that. Now, how do you achieve XP3 hybridization? How do you achieve XP2 hybridization? How do you achieve this? How do you achieve this? And how do you achieve this? Now, before we even achieve all of that, let's assume that you see a question. Let's assume you see a question. And in that question, the question says, which of the following is hybridization of methane? And then they say methane. Okay, and they put A, XP3, B, XP2, C, XP, and D, XP3D. What would be the answer? Methane. Methane is from alkane. What would be the answer? XP3. Yeah. Why? That's for saturated hydrocarbon. So for the saturated hydrocarbon, the hybridization is XP3. Please write that down. For the saturated hydrocarbon, they have XP3 hybridization. But I'm going to tell you why. For the alkenes, the double bond. For the alkenes, the double bond, they have hybridization of XP2 for the alkene. So for example, look up. For example, your ethene your propane, your butane, your pentene, and the rest of them all have sp2 hybridization. As long as from alkane, the double bond is sp2, sorry. And then your alkyne, your what? Your alkyne, the triple bonds, it is xp. It is what? Xp. It is what? Xp, yes. So if you're looking for the alkane, xp3, that's a saturated hydrocarbon. When I mean these alkanes. And then if you're looking for alkanes, it is xp2. And then if you're looking for alkynes, that's what? Xp. Now, let's now look at why it is so. And then we can now quickly go to shape of molecule. Quickly. Okay. So this may help you when you get to your 100 level, and then you'll be able to navigate well. Let's go. Now, this is how I want you to pay attention. Please pay attention very well to this place. Now, let's look at carbon. Now, why are we picking carbon? Because all these compound here, whether I say methane or ethane or propane, or I say ethene or I say propane and all that, the central atom remains what? Carbon. The central atom is what? Carbon. So we are picking carbon. Now, as we pick carbon, what do we do first? We find the electronic configuration of carbon. So let's go. What's the electronic configuration? 1s2, 2x2, and what? 2p, what? 2. You're not talking. What's the atomic number? 6 now. Hydrogen, helium, lithium, beryllium, boron, carbon. That's 6. So that's what you have here. Now, this one is called the ground state. What do I call it? The ground state. Note it. The ground state is the most stable state of that atom. That's the lowest state. Now, at the ground state, nothing has happened, but there's something here. There's a problem here. You can write that down. If it's university student I'm taking now, there's a way I would have gone deeper, because there's a way I would have been explaining. Now, at the ground state, what happened is that, because you may be asked, does carbon form its bond at the ground state or excited state? Does carbon form its bonds at the ground state or excited state? At the excited state. Why not the ground state? It is because at the ground state, only 2 electrons are available for bonding. And I need minimum of what? 4. And only those 4 can be available during excitation. And so carbon forms its bonds at the excited state. What did I say? At where? Maybe you have not even had this topic before. Have you had this topic before? You see, it forms its bonds at excited state. And so because of that, at the excited state, let's draw this. Let's draw the spin quantum number of this. Let's draw it. You know spin quantum number now? That's your 1x, 2x, your 2p. You know this now? 2p and what? 2p. So here is what? 1x, I mean 1x, 1, no, we put 1 first. 1 and then, is it still there? No, nothing will be here. Exactly. Nothing will be there. Do you observe what happened here? Nothing here. So I have filled in everything there. Please, are you following? Okay. Now, we are talking about hybridization. And don't forget, what is hybridization? The blending or mixing or 2p atomic orbital to form a new hybrid. To form what? A new hybrid. Now, so the blending, and whatever you are blending must of the same what? Energy level. So do we have 1p there? No. So it means that we cannot even touch this place. It does not have compatibility with anything. Then we can't bring in 2x and 2p. Why? Because there's compatibility of the same energy level. Are you following in place? Okay. So this one is having 2. Now, what happened at the excited state? This one is happening at the excited state. At the excited state, this one here, one of this one will jump and leave. When it leaves, what happened? This is what happened at excitation. 2py and 2pz. This place becomes filled with something. The one here has what? Has disappeared. It has what? Disappear. And so you have x here, 2x here. So it becomes x, 1x. How many p? 3p. So that's how the hybridization of the alkane are formed. That's how what? The hybridization of the alkane, that's how they are formed. Okay, so you have it that way. If you have question, please, you make sure you ask. Here, the team may be looking wine, but ask your question. Is it looking wine? Is it? Are you following? Okay, now, so let's now look at the same thing. For hybridization of XP2, how does it happen? The same thing. I can use the same thing to explain. But this is the only thing that happened in XP2. During the XP2, please listen. The hybridization here, what happened is that, please look here. What happened here is that when this one leaves and come here and come to 2pz, this 2pz, this 2pz becomes unhybridized. Write it like that. For XP2, the 2pz is what? Is unhybridized. It is not hybridized, and so we have it as 1x and XP2. You will know why. I will show you something carefully. Then when you are doing that of XP, what happened? 2py and 2p what? Z are unhybridized for XP. 2py and 2pz are unhybridized. So let's now check. Let's look at the word 18, 18, and 18. Now, 18 is like this. How many bonds do you find here? One. Abi? Okay. Now, this one bond that is here is called the sigma bond. I'm sorry, I'm going beyond your level. Please, let me just stop there. Sigma bond. Sigma bond has strong covalent bond. Strong covalent bond. Okay. So now this is sigma bond. Now, but 18 is like this. So for 18, do you observe something here? This first bond, please write it down, is called the pi bond. What do I call it? Either you write it like the pi bond. The one down is the what? The sigma bond. So it means that in 18, there's what? Pi and sigma. Are you following, please? Yeah, okay. Now, this pi bond, hello, listen. This pi bond are the one they call weak covalent bond. And it is this pi bond that gives the reactivity to this 18. You see now this one does not have it, so it's not as reactive as this one. But this one has pi bonds. It is a pi bond. And pi bonds are usually very weak, but because they can easily be broken up. During the reaction now, we can break it off straight. But we are not doing mechanism of reaction at your level. So, but I can show you now. So now it is broken up. And so this pi bond, I can take it to be, it was not hybridized. Now, when you come to ethyne, the last one, so we have this. Ethyne. These first two here are the pi bond. The last one is the sigma bond. Do you see now? Are you following now? So we have Y and Z not being hybridized. Are you getting me now? So you have your XP right there. So the XP hybridized for triple bonds, the XP2 hybridized for double bond, and the XP3 hybridized for single bond. Let's go to shape of molecule quickly as we close. Please, do you have question? Do you have question? Okay, shape of molecule. Now, when we say shape of molecule, we are actually looking at a different shape. For example, how do you do a shape of molecule? It is important you understand that. Now, methane, for example, you can write it down. Methane is called tetrahedral. Okay? Now, ethane that we just did now is called what? Trigonal planar. This one has a bond angle of 109, maybe 4 degrees. This one has a bond angle of 120 degree Celsius, or 120 degree rather. Then ethane has is linear in shape and 180 degree. Carbon dioxide is linear. Boron trifluoride is trigonal planar. Beryllium chloride is linear. This one is 180 degree. This one is 120 degree. This one is 180 degree. And then ammonia is trigonal pyramidal. Ammonia is trigonal pyramidal. Okay, ammonia is not showing. Let me write it up. That's why I have to check. Trigonal pyramidal. So ammonia is trigonal pyramidal. Then I can go on and go on like that. So on your own, tell me this and bring it to lesson. On your own, tell me this, bring it to lesson. On your own, tell me this, bring it to lesson. On your own, tell me this and bring it to lesson. On your own, tell me. And bring it to lesson. So you have 5 to tell me. 1, 2, 3, 4, 5. You tell me their shape. You tell me their bond angle. But now, how do I determine? Please excuse me. How do I determine the naming? How do I determine the naming? So that's the question here. How do I determine the naming? Now, in determining the naming, it is important you understand something here. Let me see if you can remember when I was talking about lone pair and bond pair. We have not done chemical bonding here, have we? Okay. In chemical bonding, we have what is called lone pair and bond pair. So maybe I should touch that, and in our next class, I might delve part of this. Let me show you something in chemical bonding. That's why I told you bonding is very important and all that. Now, in bonding, we have, for example, this is methane. The first thing I want to do here is to know the total available electrons around methane. That is the total around the central atom. Okay, so this is carbon. Carbon is 6. So I will say 2, 4. So I will take 4 electrons. Hydrogen is 1. 1 times 4, that's 4 electrons. So I will have 8 electrons in total. So there are 8 electrons here. And because we have 8 electrons here, and then I'm now going to draw methane. I will draw methane. So when I draw methane, let's see how it will look like. Draw methane. So you have now, this thing you are seeing here represents 2 electrons. Because of time, I want to stop here. Oh no, I would have loved to cover this thing. Okay, no wahala, tomorrow. So you have this, you have this, you have this, and you have this. Each of these things represents 2 electrons each. This thing you are seeing here. So 2 times 4, what do you have there? 8. And what do we have here? 8. That means nothing is left. Everything was used in the bonding. So here now we can say no lone pair, but 4 bond pair. So here we are 4 what? Bond pair, 0 lone pair. 0 what? Lone pair. 0 what? Lone pair. 0 lone pair, but 4 bond pair here in this place. How do I know? Because the first thing was to find the total electrons around that central atom. Okay, now the second thing I did was to now draw the layer structure, and then look at how the structure will look like. So in your own case assignment, you will do ammonia for me, find the lone pair and the number of bond pair, write it down, find the number of lone pair and bond pair. Number 2, you will do this for me, ammonia, you will do boron trifluoride for me. 3, make sure you do them before you appear in class tomorrow. Do phosphorus trichloride for me. Just do these 3. All of them are carrying 3. Let's see if they will bear the same name. So check. Number 1, the number of bond pair, the number of lone pair, and predict the name if you can. Predict it if you can. See you tomorrow. Bye.